We've learned a lot about derivatives, and now we will use them to solve something that is hopefully may be kind of useful. So let's just start with a review of the chain rule, and I'm going to write it in a different way. So let's say I had the function f of g of x. So what I'm going to do is I'm going to actually write this in a way that might be a bit foreign to you, but I think with a little bit of explanation you'll realize that this is the same thing as the chain rule that we all know and love. That the derivative, and I changed colors really for no reason, just to change colors. Sometimes I do that. I'll change colors again. The derivative of f of g of x is equal to the rate at which f changes with respect to g. So that's df to dg times the rate at which g changes with respect to x. And you're saying, Sal, this looks completely foreign to me. And one, you could think about what I just said, and I think it'll make sense. Or I could just rewrite this in the traditional chain rule format. This isn't really the traditional. What I just wrote is the traditional, but the way I've taught you. So the way I taught you, what's the change of f with respect to g? Well, that's just f prime of g of x times, and what's the rate at which g changes with respect to x? Well, that's just g prime of x, right? So hopefully this makes sense to you, that these are just two different ways of writing the chain rule. I think, what was this? This was either Lagrange or the Leibniz notation, and this is the other guy, but I forget. And this actually makes sense, just from a fractions point of view, that this term and that term cancels out, and you get, that this equals the rate at which f changes with respect to x. So with that out of the way, let's use this to solve something kind of, hopefully a little bit neat. Let's say I have a cone. We could say let's say it's one of those cups that you have at the water cooler. That's the top of the cup. And let's say the ratio of this cone, let's say the ratio at any point in the cone, the ratio of the radius of the cone, right, to the height, if this is the height, then the radius is 1/2 the height. Okay, at any point, right? As you know, it's a cone. It's a fixed cone. These are lines on both sides, so that ratio stays fixed, right? This is a 1/2 height. So just to start off with, some maybe you never even learned this. This will help us with the problem later on. What's the volume of let's say I'm filling water up to height h. Let's say this is where the water line is. Right? And I'm writing over everything I've done. But that's where the water is in this cone. Right? What's the volume? Assuming that the height is h, assuming that let's say 8 centimeters of water, what is the volume of water that I've put in the cone? Well, if you don't know it, and I sometimes, well, actually later when we do rotations of solid in the integration modules, I can actually prove this to you. But the volume of a cone is equal to 1/3 base times height, where the base is actually you can view it as the surface area of the water, right? And what's the base? Well, that's just equal to, volume is equal to 1/3. The base is equal to pi r squared, where r is the radius, right? This is just kind of a solid geometry review. And what's the radius in this case? Right? It's 1/3 pi r squared times h. And in this example that I said that the radius is 1/2 the height. So this equals 1/3 pi 1/2 the height, right? I just replaced it for r squared times h. We haven't done any calculus yet. This is just fancy. This is just complicated, not complicated, really just hairy, a little bit hairy solid geometry. And if we simplify that, we get volume is equal to, let's see, so we get 1/2 squared is 1/4 times 1/3 is 1/12. 1/12 pi, and then h squared times h to the third. Very interesting. Now let's start doing some calculus. Let's say, I think this might blow your mind, let's say I am pouring water into this cup at a rate of 1 cubic centimeter per second. And for you metric jocks, you'll know that that is also, that's, you know, sometimes doctors or nurses will say 1 cc, and that's also equal to 1 milliliter, just for other frames of reference. But I like to stay in centimeters cubed per second because we're going to work with centimeters in multiple dimensions. But let's say we're pouring 1 centimeter cubed per second into this cup. I want to know, this is an interesting question, how fast is the water level rising, right? How fast is h changing, the height of the water, at the moment when h is equal to 2 centimeters? So how do we do that? This just gives us a static picture of, if we know the height, we can figure out the volume. But if we figure it out, if we took the rate of change with respect to time off of both sides of this equation, something interesting might happen. So let's take the derivative with respect to time on both sides. So the derivative with respect to time of the volume, well, that's just dv dt. And what's the derivative with respect to time of this side of the equation? Well, it's the rate at which v changes with respect to h, right? This tells us how fast. This is v as a function of h, right? So it's going to be dv as a function. How fast does v change with respect to h times how fast does h change with respect to t, right? This is just the chain rule up here. I want you to think about this a little bit. It might not seem obvious, but all we're doing is the chain rule. It's a little confusing because I had no t's in this equation before, and all of a sudden I'm taking a derivative with respect to t. But let's just say that h actually is a function of t, which we actually know it is. So let's then just solve that. So dv, the derivative of v with respect to t, is equal to the derivative with respect to of v with respect to h. Well, that's easy. The derivative of v with respect to h is just, this is just a simple, so 3 times 1/12, right? That's 3/12. That's 1/4 pi. So we could just write pi over 4 h squared, right? So that's this part. And then let me change colors. And then this part is just still, see, I can rewrite in this new color, dh dt times dh dt. So you're saying, Sal, what have you now done? I said the rate at which the volume is changing with respect to time is equal to pi over 4 times the height squared times the rate at which the height is changing with respect to time. So can this solve the problem for us? Well, let me see if I have some space up here. Let me try to, well, I'm going to just confuse you if I go up there. Well, what do we know? We know the rate at which the volume is changing with respect to time, right? 1 centimeter cubed per second squared. So we could say dv over dt is equal to 1. I'm going to get rid of the units. Most physics instructors would cringe. But 1 centimeter cubed per second is equal to pi over 4, right? This 1 is just dv, the rate at which the volume is changing with respect to time. Pi over 4, h squared. We know what h is right now. H is 2. So it's 2 squared times 4, right? That's just, we said that h, the height is 2 right then. So 2 squared is 4 times dh dt. So this cancels out, and we get 1 is equal to pi times dh dt. And we solve for dh dt. We get, let me make sure not to confuse you, that the rate at which the height of water is changing with respect to time is just 1 over pi. Fascinating. So, or 1 over pi centimeters per second. So we could figure out what this number is. It's going to be like 0.3 something. So 0.3 something centimeters per second is the rate at which the height of the water level is going to change as I put 1 centimeter cubed of volume into this cup per second. I have probably confused you. You may want to watch this again, and I'll do a couple more videos with these rates of change problems because these tend to confuse people. But once you get the hang of it, I think you'll see that they're not so bad. I'll see you in the next presentation.